My screen is visible to everyone. May I start now? So today we are going to very good morning one and all. Today we are going to continue the second session of the chapter of your resonance, that is the series and the parallel resonance. So yesterday we have gone through the introductory part of the series and the parallel resonance. Similarly, today also a few theoretical part. Later on we will continue the numerical on the basis of the series as well as the parallel resonance. So here yesterday also we have seen how the resonance occur, how the tuning will be happening in the circuitry, what are the fundamental operations, okay, in the electric and the electronic system that divided or we are observing every day. Okay, so here the what is the reason behind that? Why we are learning that resonance circuitry, that is important. Okay, how the my elements are connected in the series and the parallel with the frequency, and we need to take care about the characteristics responses of the frequency along with the voltage and the currents. Okay, so these we have seen yesterday also. So here by looking this curve you can identify easily what the voltage and the current are increasing, both are increasing. Okay, simultaneously you will be able to observe how the frequency are increasing. So this is the peak value of either the voltage or the current here, and at that particular peak you are getting the resonance frequency. So here yesterday also we have gone through the theoretical part related to the reactances. That is nothing but the capacitive reactance and the inductive reactance. How we can calculate that the XC as well as the XL. Okay, if they are connected in the either in the series or the parallel. Okay, so at the time we can calculate easily the resonance frequency, that is either denoted by the F0 or you can say the FR. In many of the textbooks they are referring to FR, or in many other textbooks they are referring as a F0. So don't get confused. So simply we need to know about at a resonance if we are going to mention. So whatever will come under that, that will be treated as a resonance circuitry. So here we can find easily by calculating the XL and the XC. You can find the Z. Once you got the Z, the other parameter can be easily calculated. Okay, so that Z is nothing but, if you're thinking about the XL, that time you can say that Z will be the ZL. If you're thinking about the capacitor, that is XC, so that Z will be treated as a ZC. So likewise, these parameter you can calculate. Okay, this parameter you can calculate, that is the XL and the XC, to calculate the impedances. So here in the series resonance circuitry, how my components are connected, number of the resistors are connected here, how the conductor and capacitor are connected in the series, how we have what we can say, get the current flowing through the entire circuitry, and what will be my voltage drop across the entire circuit of the series resonance. So in this way you can calculate here the VS, that is the source voltage, the peak voltage, and if you want to calculate it in the form of the polar pattern, you will be able to find the angle between that. But apart from that, there is additional what we can say, the curve or the graph is there, that we are interested the phasor diagram of the series resonant, as well as we are interested to find out the power triangle of the series resonant circuitry. And if you are thinking about the phasor diagram, definitely we are interested the voltages, whether the voltage is lagging or the leading. Okay, what will be the effect of the voltage currents, okay, in the circuitry, that is of a AC circuitry, AC resonance circuitry. If you are talking about the AC, definitely sinusoidal waveform will be there, and the depending upon the voltage and the current, whether they are leading or the lagging, accordingly you will get the angle between the voltage and the currents. Okay, if but at a resonance, yesterday we have seen the condition behind that, that is nothing but the XL and the XC will be equal, and if the Z will be equals to R, it means that you are having the pure resistor. Okay, so at that time both the voltage and the current are influenced. So here see the V and VL, that is the voltage drop across the inductor and voltage drop across the capacitor, and how my voltage and the current, they are in phase for the resistor value. So similarly, if you're talking about the power triangle, that is the reactive active powers. So at the time you should take care about the quality factor also. Okay, at the time that Q will be equals to I square into X, just like for the power consumption formula. Similarly, we know very well we are having the various of the power ability, that is P is equals to I square R, P is equals to VI, P is equals to V square. They are likewise, there are the various formulas related to the power. But if you want to find out that angle in the series resonance, you should take care about the one of the parameter, additional parameter, that is nothing but the quality factor. Okay, so how you can calculate in terms of the inductor and the capacitor, that will be treated the quality factor. It is the I square of reactances, root of I square into the reactances. That is the, if you're talking about the inductor, definitely that will be XL, and if you're talking about the capacitor, then that will be your the XC. So in this way you can find the power triangle. Similarly, this curve shows the reactance versus the frequency. Here we are interested in the XC, that is nothing but the capacitive reactance. Okay, how that capacitive reactance, or we can say the XL and the XC, are dependent upon the frequencies. Okay, they are not independent. They are dependent upon the frequency. It means that whenever there is a change in the reactances, definitely there will be effect on the frequency. How they will change XL and XC? Totally they will change depending upon the value of the, or the ranges or the ratings of your L as well as the C. So in this way they will change, but definitely the effect will be happen on the frequency. So the thing, one more thing you can observe here, the capacitor impedances, that is the reactances, you can say they are decreasing, definitely the frequency will be increasing. That is nothing but they are vice versa, or you can say inversely proportional to each other. That is XL is increasing, definitely the frequency will be decreased. Second is nothing but if you're talking about the inductor, definitely if the what is inductive reactance or the impedances are increasing, so definitely again the frequency will be increased. See the difference between the XL and the XC. The XC is decreasing, the frequency will be increasing. But in the XL, if increasing, the frequency also increases. Okay, so likewise here, why it is happening? Just because we are treating the XL is greater than the XC. Here, if you are going to calculate the total impedances, that will be equals to R plus J of X. But if you want the magnitude, definitely I need to take care by getting it into the root term. So root of first term is nothing but the R square, and second term is nothing but the X square. But what will be my X? Yesterday I have told you, if my inductor is larger, definitely XL minus XC. If my capacitor is larger, then XC minus XL, like this. So totally depend upon the value of that inductor. Okay, so that is possible. So in this way you can calculate that is the impedances. Getting? So here the two curves are there. One is nothing but the XL versus the F, that is nothing but the what you can say inductive reactance versus the frequency, and the capacitive reactance versus the frequency. So see here how they are in the inductor, how they are linearly, and here the non-linear characteristics you can observe. In short, you can say the reactances are what you can say directly proportional to the frequency here, and here is nothing but the inversely proportional. And how we can calculate it, we know very well the basic formula related to the inductive reactance is nothing but XL is equal to omega L. What is my omega? 2 F. Okay, so here also the X is nothing but 1 by omega C. So in short, you can say this is the linear characteristics, and this curve is showing the non-linear characteristics. Here my inductor, or you can say the inductive reactance, is directly proportional to frequency, here inversely proportional to frequency. So in this way you can calculate the total impedance. Now here see the differences between these two. If you are going to remove this one, I square on both the side, at that time you will be able to find that is R plus J of, and this J is not having the XL and XC. If you are going to separate out, that is also possible. See here, how we can find the total impedances versus the frequency. So total impedances versus the frequency curve can be observed in the series resonance circuitry, or you can find easily by concentrating the element and the equations. How we can find the equation and the curve, that is the XL. What is the condition of the resonance? That is XL is equals to XC. So here, when the XL is equals to XC, so what will be my impedance at a particular frequency? What will be my impedance at a particular frequency is mentioned here. So obviously I am thinking about my resistor along with the frequency, the reactances along with the frequency. So you will be able to observe the curve here. That curve showing the frequency responses. This curve showing the frequency responses of your XL as well as your the XC in the series resonance, or you can say in the RMC of a series resonance. So you see here this curve is clearly mentioning the segregation. So this middle part is nothing but wherever this one curve of a XC and other curve of a linear XL are cutting on a particular point, that at that particular point I am getting the resonant frequency, that is a FR, or you can say the FC. And this previous part, here in this section you can assume my capacitor value is greater than the inductor value, whereas here the inductor value is greater than the capacitor value. Okay, so likewise you can find out easily this section as well as this section. So initial frequency and the final frequency between these reactances. Okay, so this curve is showing the reactance versus frequency. So see here, this particular. So now again the resonant frequency. This curve showing the resonant frequency curve between the two parameters, that is the impedance versus the frequency. Z is nothing but the total impedance, or you can say the impedance versus the frequency. So here you can observe the Z, how that is decreasing with the increase in the frequency. In short, you can say how I am getting my R at a particular resonance frequency, how this what you can say the impedance is increasing. So likewise few parameters you can find easily in the what you can say the resonance frequency. Which parameter you can calculate or find in the at the time of the resonance frequency? That is nothing but XL condition. XL is equals to XC. So what is my XC? XC is 1 by omega C. What is my XL? That is omega L. Okay. What is my XC? 1 by omega C. What is my XL? 1 by omega L. So likewise, you can calculate easily this omega and this omega will be omega square, and 1 by LC will be there. And if you want to square them on both the side, or if you want to calculate this omega, then that will be 1 by root of LC. So in this way, this omega again the 2 pi f. So what will be my resonance frequency? 1 by 2 pi root of LC. This formula is required while you are going to simplify the numerator. So next is this curve showing the characteristics or the curve between the current and the frequencies. Okay, how the current, this current, how you can get the maximum current if you can calculating with the help of the Ohm's law, that is I is equals to V by R. How I can get my I max. Okay, how I can get I max, that I have done yesterday also. I have explained in the previous lecture, that is a 1 by root 2, that is nothing but 0.707. Okay, to get the constant value. So this particular point and this point are nothing but the initial and the final frequency, and the range of these frequencies are nothing but the bandwidth, and this particular peak point is nothing but the resonance frequency. So in this way you can say if we plot if we want the magnitude of the current versus the frequency, at that time the fixed applied voltage will be there to obtain this curve. So in this way you can get the maximum current at a particular resonance frequency. So in the second case, we are interested in the bandwidth denoted by BW. Okay, so this bandwidth is nothing but the range of the frequency. Okay, and how I can get that resonance curve, that is nothing but 1 by root 2, that is a 0.707. We can get the peak current and the voltage at this particular moment, that is a 0.707. We can get either the voltage of the current at this peak. Okay, so in this way the bandwidth is nothing but what we can say what we say the difference between the frequencies, the range, or you can say the ranges of the frequencies, nothing but the bandwidths. Okay, so final minus initial, you can say difference between the final to initial, you can say. In this way you can calculate the bandwidth as well as the range of the frequency. Okay, so here the bandwidth will be the f2 minus f1, but if you want to calculate the f1 and f2 at a particular with resonance frequency, so bandwidth divided by 2. So in this way here you can observe the current and the frequency curve. So here the quality factor can be calculated easily. So that is nothing but the ratio of the reactive power of the either the inductor or the capacitor to the average power. So what is that quality factor? Quality factor is nothing but you are the what you can say the reactive power or either the inductor or the capacitor average power at a particular resonance circuitry. So here the reactive power, okay, the inductive power, that is nothing but the what can say the XL divided by R, and what is my XL? That is omega L divided by R. What is my omega? 2 pi FL divided by R. Here we need to take care about which particular frequency we are using, that is nothing but the resonance frequency. Again, the ratio is nothing but either you take as the bandwidth, the ratio of the resonance frequency divided by the bandwidth. If you are not having this value in the numerical, at that time you will consider either the XL by R. Okay, so how you can calculate the bandwidth? If some in out of three, if two is given one unknown parameter, you can calculate easily. So in this way, these are the few formulas by which you can find out the unknown parameters. So here the what you can say, this curve is the representation of the voltage drop across the each component along with your the frequency, you can say. So we know very well we are having the three components, that is the R, L and C. So voltage drop across the capacitor is the VR, voltage drop across the inductor is the VL, and the voltage drop across the resistor is VR, VL and the VC. Likewise you can find out with respect to the frequency this curve is showing. So here by applying the here the KVL to the circuitry, okay, if what is the KVL, if you are applying the, then that time you can upload the things, okay. So how you can get the range of the frequency, how you can get the bandwidth, what will be my resonance frequency at a particular point, initial and the final frequency ranges, and we also need to take care whether my voltage is lagging or leading in the capacitor or the inductor. Similarly, I should take care about my whether the I am getting the minimum or the maximum current. Okay, so here if you are getting that maximum voltage across the capacitor, definitely my the voltage drop across the inductor will be the maximum. How you can get this one? With the help of the voltage drop across the each along with the quality factor. So here the information again, as per the resonance circuitry, you can say the VL is equals to VC because XL is equals to XC. So definitely the voltage drop across the inductor and the capacitor will be equal. So now go for the parallel resonance circuitry. All are connected parallelly. That is R and C, and you are applying the voltage drop across this one, and the current will be divided from each branch. The current will be different in the R, the L, and the C. So here, see, in the there is no as such difference between the series circuitry just because there is no division of the current. But while you are studying the parallel resonance circuitry or the parallel circuitry, definitely there is a the current is dividing in the each branch. That's why we need to take care while you are going to simplify the circuitry. So here one of the circuitry is see here the difference between all the circuitry. In the first circuitry, R and the L are connected in series and the capacitor is across that. This is the one case. Similarly, okay, similarly, what is going on here? This we are going to simplify. Okay, so let it be this. This is the first case. Similarly, R is parallel with the L, is parallel with your C. Means all are equally parallel. That is R, L, and C. Okay, so see the difference between this circuitry and this circuitry. This is the simplified circuitry from this one. But if you observe, this is A part, this is the B part. Okay, you can say like this. Fine. So what is going on here? The R is in series with your the L. Okay, just like your the SC network or the oscillatory network. Okay, R and L are connected in series, whereas the capacitor is across that one. How we can simplify? We can simplify first this circuitry, then later on L1 parameter you will get that you need to note on here, and the other you can find easily. So likewise you can get. So here we know very well for the R will be as it is. For the L, we always used to note down the XL. Okay, and for the capacitor, we note down the XC. So what is my XL and the XC? You know very well. Okay, so just apply here the things which is there. Okay, this is the derived expression. Okay, this is the derived expression. Already we have derived how we are getting each and everything. How my current will be flow through this particular branch, to this particular branch, and this one, and what will be the effect. So likewise, if you are can say simplify with the help of the quadratic equation and all, you will be able to find directly this the equations. That is nothing but the RP is nothing but the parallel register. That is a combination of this branch register to the XL square means particular this RL. You can say RL square plus XL square divided by RL. Why I am taking this RL? Because I can't say this is my RP total. Okay, total will be this entire RP. RP will be, that is a parallel register will be entirely this entire. But if I want this particular this branch, so I have given the notation of RL square. Okay, RL simple. This RL square into your this one divided by summation. Okay, so summation is nothing this into this. Why we are taking this one? These two are connected. The how we got this RP, that is RP is equals to the particular RL into, okay, RL into this one divided by this one. So similarly, you can calculate the inductive reactance and the capacitive reactance. Or we can calculate the inductive and the capacitive reactances. That is also mentioned here. Okay, so here this is RS is nothing but your the what you can say, the source registers, which is across the current and all other. This section is different. This section is treated as a source section. This circuitry is no other section, that is a RLC circuit connected parallel or resonant circuitry. This is the source circuitry. Okay, so in this way, if there is a connection in series, so that time you need to take care about the impedance. If the circuitry is in the parallel form, you need to think about the admittance. Okay, so in this way, this R, L and the C are connected parallelly. So after reducing the circuitry, you will get like this. Okay. So at that time you can say your RS, that is a source resistor, is parallel to the RP, and this RP is nothing but the combination of R, XL and XC. So in this way, this RS will be the parallel to this entire circuitry. Okay. In this way, we calculate easily conception of the parameters. Okay. So what will be the case in the parallel resonance circuitry? How you can find the power factor? Okay, at a particular frequency. So at the time, this parallel resonance frequency will be the resonance frequency into the root of 1 minus R square into C divided by L. Okay, how I can get the maximum impedances? Okay, so how we can get the maximum impedances with the maximum impedance with the concentrating the resonant frequency along with it. These are the derived formula expressions. Okay, so in short, you can say the resonant frequency is greater than this. What we can say the power factor frequencies as well as the maximum impedance frequencies. So this is one of the curve which is showing the characteristics between the impedance and the frequency in the parallel resonance, especially in the parallel resonance. See here the one of the two. In the series that is started from the zero, but here just because of that the combination of the parallel circuitry, here there is a RL. So here after a few values of impedances, the curve will be start to increment. Okay, so here the impedance versus the frequency characteristics is shown here. Okay, how you can get the power factor frequency ranges along with the maximum or you can say the peak of frequency ranges by concentrating the value of the impedance. This is also one of the peak value of your the voltages, how the my voltage across the parallel circuitry can be lead. Okay, here at the starting that is a leading and later on it's a decreasing. Okay, and reaching towards the final frequency ranges. So here this part which is from the lead to lag. Okay, so circuitry is inductive just because of the lagging. Obviously, so from the lead this particular 90 degree that is lagging and coming up to the 0 degree. So likewise this portion will be treated as a inductive or you can say the lagging portion. And the other portion which is leading. So in between the leading and the lagging, the particular point of the section is nothing but the resonance will occur at this point. Okay, so that resonance circuitry is by concentrating the parallel circuitry, that is nothing but the FE you can say. Okay, so in this way, this is the inductive portion, just the lagging. Okay, the current is always lagging in the inductor, whereas the current is always leading the capacitor. So this is the leading part with respect to the current. This is the lagging part with respect to the current in the inductor. Okay. So if the current is lagging here, definitely the voltage will be lead in the inductor. If the current is leading in the capacitor, the voltage will be lag in the capacitor circuit. So that is the current. So here the effect of the quality factor. Okay, what should be the quality factor? How we can get the sufficient of a large quality factor by observing the series amplifier as well as the parallel. For the series, if you are concentrating, so already we have done Q is equal to 1 layer root of L by C. But if there is a parallel resonance circuitry, at the time you need to take care because the each branch current is different. So here again how you can calculate your the XL and the XC. Okay, in the what you can say the parallel circuitry. Okay, so here will be your the parameter will be changed. The book to book the notations are changed. Okay, so this RP is denoted by the parallel register. This ZTP is nothing but the total impedance in the parallel circuit, and the QP is nothing but the quality factor in the parallel. So here, if simultaneously in one of the numerical, if A and the B part is mentioned for the one, A is for the series and the B is for the parallel. At the time, you need to take care of about the RS for the series, RP for the parallel, ZP for the parallel impedance, and the ZS is nothing but for the series impedance. Similarly, quality factor for the parallel and the quality QS for the series quality factor. Like this, you can calculate the parameters of your the reactances. So in this way, you can also find the bandwidth, the range of the frequency. Already we have discussed. Only the change is in the parallel circuitry, what will be the effect? Okay, how my total current can be divided into the each branch, that is R, that is XL, and that is XC, that is the current flowing through the XL, current flowing through the XC, and what will be the voltage drop across the each one. So in this we can calculate like this. Okay, and also you that is nothing but the current flowing through the inductor, current flowing through the capacitor with the help of the quality factor we can find this. So this is the summary table you can say in the parallel circuitry, and this is the what we can say resonance frequency 1 by 2 pi root of LC of this resonance frequency in the series circuitry, and in the other case what is the difference between these cases. Frequency is changing in the parallel resonance just because of the circuitry is dividing. Okay, so every time just because of the connection of the RL, one time combined, one time separate out. That's why the frequency resonance is, it changes every time. So in the second case also you can find easily the impedances how my RS is the parallel toward the RP, and this the RS will be connected. So in this way you need to take care along with your the reactance is the quality factor also. Okay, so here Q1 and the Q1 is greater means how I can segregate my Q quality factor, whether at any Q what will be my case if my Q is greater than the 10, if I am getting the more than 10 value at the time, what should be my case. So depend upon the circuit connected and depend upon the value of the obtaining that quality factor. In this way you can find easily in this summary case. So here, if you have a calcium, all of you will start in the numerical way. So few numericals I have mentioned here, how you can calculate that you will see.